Hey guys, so in this screencast, we'll discuss the nodal analysis. So, in this problem, we have been asked to come up with IO and V2. So, how can we use the nodal analysis? So now, under the nodal analysis, the nodal analysis is simply it is the modified KCL. So we use the KCL to come up with using the KCL equation to come up with the nodal analysis method. So in this case, the basic thing to know is the KCL. So we need to assign the currents first. That's the first thing when dealing with nodal analysis. So we need to assign the current. So I'll redraw this circuit, this page. So here we are. We do have this. This is our circuit. This is 6 volts on 12, positive, negative, 2Vx. This is V2, this is V3, and this is V1. This is 6. Here we have got 6. Here we have got 6 again. So again here we have got 12. So I'm going to assign the currents. So the currents we have got this as my I1, then this as my I2. This, so you can name them the way you want. So this is I3. This again is I4. So those are the currents. So whenever there is a resistance, a resistor, we assign the currents. So now starting to analyze this circuit, what can we see? What can we see from this circuit? So from this circuit, we have got a voltage source. So whenever you have got a voltage source in parallel with a resistor, what we should know is that we have got a super node. So this is a super node. This is a super node. The all of this starting from this point to this point, it is a super node. This is what we call a super node. So there at a super node, what we need to know, we need to determine, so this is a super node. So it is in parallel with this resistor. So whenever we have a super node in the circuit, first of all, the thing that we should know is we need to know the currents entering the super node and the currents leaving the super node. So we know that all these currents, I1, I2, I1, I1, which is here, I3, even I2 and I4. These currents are all leaving the super node according to the way we have assigned. So there is no harm in assigning the currents. You can point them whenever you want. So but according to the way we have placed them, they are all leaving the node. So meaning their sum must be equal to 0. So we are saying I1 plus I2 plus I3 plus I4. This is equal to 0. So what else do we need? So having this KCL equation, we now need to start replacing with the voltage and the resistance. We need to replace the current so that it is in terms of resistance and voltage. So we use the equation, the Ohm's law. Let's say we say current is equal to V over R. We say current is equal to voltage over resistance. So in this case we say where there is I1, so I1 is the same as saying V1 over 12, where there is I1. So if you are asked to calculate the current across this, we say it is simply this voltage dividing the 12 ohm resistor. So there we go. So there we go. Plus where there is I2. So our I2 is equal to what? So which one is our I2? Okay, our I2. Our I2. How many I2s do I have in the circuit? Oh, this is I4. Okay. So our I2 is equal to we have got V2 over 6 plus our I3 is equal to we have got, so our I2, our I3, let me go back. This is our I3. So you know that there, where there is I3 is coming from V1 and going to V2. Going to V3 there. So it is leaving V1 and entering V3. So, but what we should know is that in all the problem that will be tackling under this, we must know that current will be flowing from the higher potential going to low potential. So meaning we subtract the voltage at low potential from the voltage at higher potential, and then divided by the resistance according to the Ohm's law. Yeah. So in this case, what we are saying is we have got it will be so I3 will be equal to V1 minus V3 over 6 plus we have got I4 there. So I4 is coming from V2 going to V3, meaning V2 is at higher potential, then V3 is at low potential. So this is equal to V2 minus V3 over 12. So all this is equal to 0. So what can we do? So here we need to come up with a common denominator. So we can multiply the whole of this throughout by 12, since 12 is the common denominator. So multiplying by 12, we get we have V1 plus 2V2 plus V3 minus V. So we get there, we need to have a 2 in front again, because 12 divides 6. If I multiply a 12 here, I'm getting a 2 on the bottom, on top. So we get 2 V1 minus V2 plus there everything will cancel. The 12 will go into 12. So I'm getting this, so V3 equals 0. So if we were to reduce this by correcting the like terms, we get V1 plus V plus 2 V1 plus V1. So here we get So there we get how many V1s do we have? How many V1s do we have? So the number of V1s that we must get there, we are getting. So we are getting. So this one is not supposed to be V1. I've made a mistake somewhere. Okay, this one is supposed to be V2. Okay, so this one is supposed to be V2. So I'm getting, let me wrap this. Okay, so I'm getting V1 plus 2 V2. What I'm getting is, I must get 3 V1. I move now to V2. So V2 here, I've got V2 there. This again is supposed to be V3. Okay, so I've got V2, 2 V2, plus V2. I'm getting plus 3 V2. Then I also have minus minus 2 V3 minus V3. So I'm getting minus 3 V3. So the O of this must be equal to 0. So we can divide throughout by 3. So dividing throughout by 3, I'm getting V1 plus V2 minus V3. The O of this must be equal to 0. So this is equation 1. So that is my equation 1. So having that, what we need to know again is, let's go back a bit. This voltage V3 is equal to this 6 volts. This 6 volts, yeah. So V3 is equal to 6 volts because in this region we don't have any resistor. That will cause the voltage drop, so that at V3 we have got a different voltage, but it is just a wire with a voltage source there. So meaning V3 is equal to 6 volts. So whenever there is V3, we are going to replace with 6 volts. So there we go. So I'm saying we have got V1 plus V2 minus, where there is V3, I'm replacing 6 equals 0. So V1 plus V2 is now equal to 6. So this as my equation 1 now. Yeah. So let's go to the next step. So the next step is from the circuit diagram. Let me draw this. We have got this there between V1 and V2. We have got that voltage source, the dependent voltage source, which is 2Vx. That is the value. Then here we have got V1, and here we have got V2. So if we assume current to be flowing in this direction across the voltage source, if we assume current to be flowing in that direction, let's say this is I. If we assume it to be flowing in that direction, then it is flowing from the higher potential V1. So we know the current there is entering the positive terminal. So whenever the current is entering the positive terminal, because we know in the assumption we are saying it must flow from the higher potential to the low potential. So now in this case, by it entering the higher potential, it means it is flowing from the low potential. So what we are expecting there, since it is entering through the positive terminal, what we must expect is there is a voltage drop. So if it was entering through the negative terminal, then it was supposed to be a voltage rise. So now it is entering through the voltage through the positive terminal. So we have the voltage drop there. So we have minus 2 Vx. So current is voltage is dropping. So minus V2. So this is supposed to be equal to 0. So having that, so the next thing is so what is Vx back? What is Vx? So I'm sure I forgot to put this. Without this we can't solve this. So here this is Vx. So Vx is the voltage across the 6 ohm resistor, is the voltage of the 6 ohm resistor. So here it is Vx. So yeah. So Vx, so in this case Vx is the voltage across the 6 ohm resistor. So now voltage across the 6 ohm resistor is the same again as V2. So it is the same as V2. So Vx is equal to V2. So there we go and replace again. So we replace that again. So we say we have got V1 minus 2V2 minus V2. This is 0. So there we have V1. There we have V1 minus 3V2 equals 0. So we get V1 is equal to 3V2. So this again as our equation 2. So we now have everything in terms of V1 and V2 according to the equation we have. So the next thing that I'll do now is to solve these two simultaneously. Because I know that V1 is V1, equation 1 is V1 plus V2 equals 6. So I'm going to replace wherever there is V1, I'm going to put 3V2. So there I'm going to replace, I've got 3V2 plus V2. This is equal to 6. So I've got 4V2 equals 6. So what am I getting? So I'm getting so I'm getting so I'm sure this, what is this? So need to wrap this, shouldn't be part of our work. This is not part of our work. So if that is the case, so I'm getting V2 equals to 6 over 4. So V2 is equal to 1.5 volts. So if this is the case, according to the demand, I have answered part one of the one of the tasks that have been given. So out of IO, so IO, let's go back to our original diagram. So this is our IO. So our IO is the voltage across the 12 ohm resistor there. So we need to come up with V1. We need to come up with V1 because what I know is that current IO is equal to V1 over 12 ohms. Yeah. So meaning if so we need to come up with V1. So V1 there, I know that from the relationship that I had previously, V1 equals 3V2. Yeah. So my V1 there is supposed to be 3 times. So my value of V2 is 1.5. So V1 is equal to what is 1.5 times 3? I get 4.5. So my my I0 is equal to 4.5 divided 12. So what am I getting? So I'm getting 4.5 divided 12. So I'm getting 0.75, 0.375 milliamps. So this is the current that I'm able to get. So I've got IO equals 0.375 milliamps, and V2 equals 1.5 volts. So then we have answered. So thank you so much, guys. We'll meet next time.